All right, so let's work an example. Let's find the stiffness matrix for this triangle. All right, what's the first thing we need? Oh, that's a good point. We do need numbered nodes. But okay, 1, 2, 3. That's a good point. So with those node numberings, the first thing we have to decide on is, I only gave you 3 nodes. The triangle didn't have interior nodes, right? So if I only give you 3 nodes in a triangle, what's the interpolation going to be? Yeah, linear, right? I have to give you more nodes if we're going to go higher order, right? So for a triangle, I have an interpolation field that's 1, x, y. All right. I have an A matrix that is going to be x evaluated at where? For the first node.
0, 0.
Second node?
A, 0.
Third node? So my shape functions are x dot inverse A, right? Right. So, and again, we could have just written those down from the formulas that we showed last time. The beauty of Mathematica is it probably would have taken me longer to type them in than to solve for them. Right? So I have those are my 3 shape functions, but I need to construct this shape function matrix, right? So that is what? It'd be n 1, 0, n 2, 0, right? But I'm lazy. There's a better way to do this. I can just define a matrix define a constant array of zeros that's the length of nn. Need to figure out how to just change the whole notebook. And then Mathematica has this cool function called riffle. So I'm going to riffle nn with zeros, and then I'm going to riffle zeros with nn. There we go. So can everybody see what we got? Right, so it's n1, 0, n2, 0, n3, 0, 0, n1, 0, n2, 0, n3. So that's my n matrix, right? So now I need to define the strain displacement matrix, because remember, we're looking for the stiffness matrix, which is B, B transpose times B, It's B transpose times C times B, where B is this so-called strain displacement matrix, right? Well, the first thing I need to do is define that differential operator matrix. And I can use some tricks in Mathematica to make this easy for me. So before class, I was showing the guys this thing called a pure function. I'm going to use that to my advantage here. So basically, I'm building a differential operator matrix, and I'll show you how I use it. So just real quick about the syntax that I'm using there. When I use this pure function notation, so if I say that d of hash with respect to x and, so I just defined a pure function, and what I can do then is I can then map that over a list. So for example, if I have x squared, x cubed, what I mean is I'm going to take and map this over that, right? Such that I get the derivative of x squared, and x cubed, right? So this is the differential. This is the derivative operator in Mathematica, right? So the derivative of that thing with respect to x. So I'm just going to put that there, put that there, put that there, right? And so that's just the syntax. And so if we, sorry, it should be a, there we go. 1, 2x, 3x squared. Okay? All right. So with that, I'm going to use a little trick. Mathematica has this very generic differential inner product, very generic inner product matrix. Okay. So what this, I defined another pure function, and this pure function is going to take the first argument and place it there, and the second argument place it there, and then it's going to take the inner product, or the matrix multiplication, right? So I have this differential matrix D, right? So that's going to be D of x, and then replace it with the first term n of x, and it's going to compute that. So this right here is n1 with the derivative of n1 with respect to x, and you can just see that, right? And so I just constructed the whole thing in one little shot. Use the trick. Of course, you could do it by hand, right? This is really easy. Okay? So now I have my B matrix. My C matrix is just constants, right? So we'll just C11, C12, 0, 0, C12, C22, 0, 0, 0, C66. All right. So now I'm going to integrate over my triangle. And the integrand is going to be B transpose C B, right? I want to integrate dy dx. What are my bounds of integration for the triangle as I defined it? Well, the slope of the triangle is b over a, right? Times x. Okay. So that's in the y direction. And in the x direction, I go from what? So there's our element stiffness matrix.
When you put the dots there, does that mean dot products?
Mathematica is smart enough to know what you want to do if it's a, it's an inner product. So if it's a matrix and a vector, it's going to do an inner product, a matrix vector multiplication. If it's two matrices, it'll do a matrix multiplication properly. Yeah. If you had like just a multiplication, it would be element-wise multiplication, and your data structure would have to have the same shape. So if it was two 3 by 3s, it would just do element-wise multiplication of that, right? If it's a 1 by n, it would do element, but you couldn't do like a 3 by 3 times a 1 by 3. It wouldn't know what to do with that. But if you use the dot, then it uses the dot product. So why is our stiffness matrix? We only have 3 nodes. In the last time we developed a stiffness matrix with 3 nodes, it was a 3 by 3. Why do we have a 6 by 6? Yeah. You have 2 displacements now at every node, right? So before we were working with scalar fields, right? Temperature, pressure, right? Now we're working with displacements, which is vectors. Okay? So I think in the interest of me not being late for my talk at 11, I better go because I have to walk across campus. But so we'll stop here.